Hello, my dear friends. This is Dr. Mohamed Nezami coming to you again from Jerash, Jordan. Um, this is the second part of my design of optical front-end receivers. As you might recall, this is basically this is my YouTube channel from which I come to you from. The I have please, if you're watching this for first time, please subscribe to the channel. I would appreciate it. This is the first part where we talked about the
Hello, my friends.
where we talked about various parts of the front end of optical um, um, receivers, front end receivers. Please refer back to this because today's part is built on what was done then. Okay, so I'd appreciate if you go back to that and then watch that and so you can get the full story. Okay, so today let me put this in full screen. We're going to cover the second part. The first part primarily was dealing with the transimpedance amplifier. Well, okay, before I get to that, let's get some uh, uh, information on my services. I am a freelance RF and microwave board level designer. Um, if you need any work with board levels, routers, or whatever high frequency and RF and microwaves. I work with clients remotely, designing from here, from Jerash, Jordan, what you see behind me. Um, I work with you very reasonably because I operate not in Western Europe nor from the United States. So I operate very inexpensively. I work with you from concept all the way to handing over to you the PCBA manufacturing files and so forth. So if you have any projects, if you're in need for a portion of the project, or if you have an existing board that you would like to that has some obsolescence in it that you need to modernize with new parts, I can work with you on that as well. But primarily working with you from concept to drafting specifications to signing a consulting agreement with you, NDAs. Um, and then I basically work with you and your team on the design. I work completely from concept to BCBA to fab files. And then I also support you through testing and verifying and taking to production or integrating. And if it needs to, then we can go ahead and respin the boards. I could do that as well. Okay. All right. So let's go further. As you can imagine now, optical sensors and devices are everywhere. So primarily a lot of lasers and visual and infrared and and then for every one of these devices you might see in the icons in here as there's so various some military and industrial and communication devices that requires an optical front end. And so basically, um, this series deals with taking either a laser diode or photodiode or a silicon photomultiplier, SIPM, and then basically building a low noise front end, okay, which is very similar to building an RF receiver, except we're really dealing with analog. And toward the end of the day, we're going to get to a point where we're going to introduce the third part in this series, in which we will completely work with radio frequency. Because as you can imagine, these sensors are getting wider and wider in bandwidth, so they're requiring to use multiple gigahertz ADDs sometimes in some of these sensors. especially for defense and for remote sensing. So we will introduce that, and then the third part we will get back. Basically, we'll start talking about S parameters and the classical radio frequency design approaches, rather than dealing with high-speed op amps and analog and DC. Now, optical devices, as you can see here, they vary from pigtailed fiber optic front ends, basically pin avalanche photo detector, and then laser diode and SIPMs, and here photodiodes, and so forth. So basically, the receiver front end is to take one of these devices or multiples of these and build an electronic front end circuitry that will present the signal and preserve its signal to noise ratio to the analog to digital converter or some other detectors as well. Okay. This is a block diagram just showing basically the typical and this block diagrams from analog devices. As you can see in my presentations, a lot of times I try not to redraw figures, but I just grab them from here and there because there is really no need to. The focus is not to create these figures, but to present the concept. Okay. And so in a typical optical front end, you've got the optical sensor in here, and you've got an analog to digital converter in here, and then your DSP in here. And so in between the digitizer and the photodiode, there's a chain of blocks that you would need to use depending on the application. But primarily, most of them, because you're really trying to detect a current through an optical device before you establish a voltage a level. Mostly, it's a transimpedance amplifier in the front end that will take the current and preserve the signal to noise ratio and present some kind of voltage. And then, of course, because of ambient noise from visual light and other things, you would need to filter that as well with a simple either LC or just an RC filter. And then, of course, you need at that point, this signal in here is preserved as close as possible to the actual signal being received, except with a little contribution of noise from this device here, and that's the third lecture in this series, where we will talk about the signal to noise ratio from that between the what you're picking up and what you have in the digital domain. And then at that point, that voltage level in here needs to be brought up so that it can be seen within the ADD. Okay. Now, the ADD is designed to see signals between its ground and its reference level. Okay, which is the reference in here, and that reference basically is a reference voltage that you have to provide usually to these ADDs, and that reference is used also for the ADD driver, which is this one here is we're going to talk about today. Last time we talked about this device here, so today we're going to talk about mostly this device in here, how to interface to the ADD, and preferably differential, but you don't have to. In a lot of cases, we don't do differential interface between the ADD and the ADD driver from the optical device. So we'll talk about this today, but this voltage reference is also shared by this device and this device, these active devices. And the reason we do that, for instance, in this device here, if it's differential, we need to use a common voltage in here, common mode voltage for both of these signals, okay? And to do that, we need to share this. We don't bring one from elsewhere, so that any deviations in this or any changes due to temperature, they will also track in here. Because essentially, the reference voltage that comes into the differential analog to digital converter interface driver usually um, is the midpoint in the digital domain. That's where, if you view your captured data, um, above that reference is basically all positive. The most significant bit will always be zeros, and then below that it'll always be ones, meaning it's negative, or vice versa, as long as you keep track of this. And then I listed in here some of the basically the the parameters that we're dealing with. These parameters in here that deals with the digitizer as far as full scale power, the number of bits and the effective number of bits, quantization noise level, signal to noise ratio, quantization noise, and it's Nyquist bandwidth, or its actual capture bandwidth. The same thing for the optical sensor in here. We have these here, basically. And then we have these here. We introduced these last time. Okay, so like I said, okay, if you look at the chain from the optical sensor to the ADD, you're going to see a bunch of devices. And what happens is the signal, you can track the signal to noise ratio and the signal levels between the ADD and the sensor. And this lecture today, we're talking about this driver in here. We covered last lecture, we covered this transimpedance amplifier. But what we're really trying to do is trying to somehow build an interface between the sensor and the ADD and preserve the signal to noise ratio. And in the RF domain, of course, in the RF world, we want to try to preserve the dynamic range and the noise figure so that the signal in here is preserved as much as possible and presented to the ADD. Now, the ADD, of course, has a noise floor, which is its quantization noise. And then the sensor has its signal has a noise floor, which is the thermal noise. Okay? Now, and so the trick is to for the chain in here is that you would want to amplify and filter the signal so that by the time it gets to the ADD, it's at least above the quantization level by a certain margin. Some people use 3 dB, some people use 10 dB, and the reason for that is because we want to make sure that the ADD we're not incorporating any noise from the ADD. Which means what you want to do is you want to figure out what is the quantization noise level for the ADD, which is a plus minus one half least significant bit. And so figure what that in RMS, and then so make sure that your noise floor in here, the noise spectral density in here, is actually above or equal to the spectral noise density of the quantity from the digitizer. And this is graphically shown in here. So you can see that at this point we've got the background noise, okay, thermal noise, and the signal, okay? And then we go through the TIA, which has certain noise figure, okay? And what will happen is that this noise floor in here will get elevated um, by a certain amount, which is equal to the noise figure of this amplifier, just like in a classical RF, typical RF chain. And then your noise now is amplified by the noise figure of this amplifier. So, and your signal is amplified by the gain of this. So the trick is to try to maximize your gain so that this noise here does not eat up from your dynamic range, okay? And then, of course, because it's a broadband noise, we try to limit it a little bit. So we have a low pass filter in here. And we basically chop off some of the noise in here, some of the high frequency noise. But primarily, this also blocks any harmonics or interferences that could come in here, other than the broadband noise that you're getting. Okay, so and then we go further to this driver in here, which we will cover today. And this driver in here, its function basically is to try to take this signal in here, which is this, present it to the ADD with a match dynamic range, meaning that the signal, once it gets to here, it has a certain dynamic range from min to max. you would want this to line up with this. And the way to do this is we incorporate some common voltage, some DC voltage we present here so that we're in the middle of the A to D range. And then whether the signal goes above that or below that, we need to make sure that's amplified enough so that it's being between the full scale, the most significant bit in here, and the least significant bit in here. So we don't do the anachronism. It does not do you any good if your signal in here, for instance, is between, say, um, 0 and 1 volt, and your ADD range is from 0 to 5 volt. As you can see, you've lost a lot of dynamic range. It does not do you good, for instance, if this signal in here has a DC common voltage, say 1 volt, okay? So, and then your signal is plus minus 1 volt, which means this is going to see from 0 to 2 volts. And so today we will work through some simulated um, circuit examples that shows you how to do that. So, but in any case, once the signal gets in here, as you can see, it accumulates, it adds another level of noise, which is FDA, which is the full differential amplifier. That's the name given to the typical circuits like this. Okay. And these are from basically from literature from ADD, just borrowing the diagrams, okay? And so in the ADD now, once you get to the ADD, you digitize it. Now again, the ADD has its own noise floor, and that's what where you end up with another additional level of noise. So now you measure all of this noise accumulated in here, integrated over. And then you have signal in here, so you can figure out your signal to noise ratio in the ADD. So as you can see, this analysis and design of this front end is extremely critical because it would not do you any good to have a multi-million-dollar sensor and then thousands of dollars ADC analog digital converters and then not preserving or not seeing most of the signals because you've got uh, parts that are dollars and dimes and you ruined your dynamic range or you distorted your signal. Okay? So pictorially, this is just showing a figure in here where we're showing the TIA typically, which we did last session. Please go back to that last session and watch it before you do this. And then you've got a little low pass. And then at this point here, the signal usually single-ended, okay? Meaning it's reference between this voltage and ground, okay? And most of these sensors are single-ended. So, and the ADD, of course, it's it's differential to benefit from the characteristics of a differential circuitry, which is we will get to right now in a moment. But primarily is to reject common noise that comes in to the positive and negative parts of the signal in here. And canceling even harmonics as well. So basically, this here is fully differential FDA, fully differential amplifier. Is basically takes the signal that has been amplified and filtered from the photosensor, and then basically converts that from single-ended to differential, meaning two wires instead of single wire. And then at this point here, this is an additional low pass filter. This is for anti-aliasing filter, they call it. Now, even though it was drawn in here as RC, this is more complicated than this. It can involve ceramic filters or other form of filters, and high frequency filters. All right, so let's go further. So now, as you can see in here, another concept which is beyond the scope of this lecture is this signal, depending on the sample frequency that you're going to sample, and depending on the center frequency of the signal that is being picked up by the optical sensor. Now, you're in the digital domain, your information has multiple replicas, basically. So you can actually try to tune into any of these ones. And that's what we call Nyquist zone. Okay. And that's basically the first Nyquist zone is at a half-wave distance between the sampling frequency. Okay. That's gigahertz sample frequency in the case of multiple gigahertz digitizers. And then the half sample frequency. So you got one in here, half, and this, of course, there's in the negative in here. Okay, in the digital domain, it's really the negative portion is still shown. So now this here really determines a lot of times the filtering that takes place in here because that's basically trying to um, your signal coming in at a certain frequencies and you want to make sure that you don't get any aliases. So if you're doing DC coupled, meaning you're using a first zone, you would want all these filters to try to work hard at attenuating any of these components because any of these components will alias back and fold back into your so let's get back to last time. Last time, what we did an example of this TIA in here, okay, using this high-speed device from TI, Texas Instruments. And then we use a voltage to voltage amplifier in here. So this is a transimpedance amplifier. You can see that because you don't have any resistances in the source. So basically you have a current coming in from the optical device, which is presented as a current source in here. So it goes in and establishes a voltage based on this resistor. And we talked about the stabilities and this is the parasitic impedance, capacitance of the both combined between the amplifier package and the sensor. And then what we need to do, we amplify. This is a 10 times the voltage from another device in here, okay? And we said if we, for instance, this is a fit between this here, this signal is plus and minus 50 microamps, which is as a square wave in here. And that's basically the VF1, VF2, that's the signal from here to here. So first one in here gives us to plus and minus 30 millivolts, peak to peak, zero to peak, sorry, or 60 millivolts, peak to peak. And then get amplified 10 times, and that's where we get close to 200 millivolts, which is this one in here, okay? So let's take this circuit, okay? And let me go to the simulator basically, and we're going to look at that first circuit. Okay, and that's not this, but okay, that's this one in here. So this is the circuit that we looked at last time and designed and analyzed. And just to refresh your stuff about this. This is basically, as you can see, the frequency response in here. So uh, it's got a little peaking in the gain, but we can treat that later. Okay, and I showed you the methods to do that. And then, of course, if we look at the AC signal coming in, it's basically like this. So this is the signal in here. So what we have in here is a signal that is between so it's between minus 0.25 volts to 0.15 volts, okay? So, and the DC level in this signal basically is this point in here, which is 100 millivolt, okay? So basically, and then if we look at this, this is DC coupled. So if you look at the DC transfer function, okay, and of course this is how many, let's see, this is a square wave with 50 microns, so microamps. So let's adjust this. Oh, yeah. Okay, this transfer function, this is 50. This is 100, say. And adjust this. Look at it and broaden the window. Look at this. Okay, so basically we've got the first stage in here is our signal. We look at from minus 100 to plus 100 microamp, and we get the voltage in here. It's an inverting amplifier, so we get the voltage between 50 millivolts to minus 50 millivolts. And then 10 times that is the second stage in here. And that's basically where we get 500 millivolts, okay, at the maximum from minus 500 to plus 500. So this circuit works beautifully. And so what we need to do now is we need to take this here and go back to our chain in here. That's this device. And for leaving out this for a moment. So we're going to take this in and try to present this to a certain ADD. So you grab an ADD that you want to use, and from the specifications of this device in here, you would want to amplify basically this signal in here so we can build up this for a certain ADD. And that's the concept we're going to talk about today. So let me close this here. Okay, so let's get back. So the first thing we want to do in here, of course, is the ADD itself. If you look at the ADD in here, this ADD, the first thing is that this ADD, you design it with the interface such that it has some kind of range on the input in here. You designed that based on the DC references that you present the ADD with. So what we need to do then, our task is designing this ADC driver our task will be just to basically match the sensor range in here and a sensor giving a sensor output in here, sensor range. And that's basically involves both gain and DC level shifting. Okay, and that's what we are going to look at today. So pictorially, let's present this idea here. So basically, what we have a sensor, we have an amplifier, and an ADD. Okay, the signal and what is done in here is that we are presenting the sensor output span and then the ADD output span. And usually you have a maximum voltage that the ADD will basically overflow, and then a minimum voltage that the ADC can see. And that's what we want to do is we want to make sure that we are utilizing that range so that the transducer signal, dynamics of the signal in here, when it's minimum or maximum, it still can be captured. And we don't want to, and that has to be optimized so that you don't lose any of the dynamic range that the digital RS has. So imagine this: if you have a sensor, let's say that gives you between 0 and 3 volts, and this meaning this really here is out of the TIA or the full system. And then your ADD is designed to take a signal to see a signal between 1 volt and 4 volts. Now, what happens is that this one in here, the dynamic range of the signal in here is 3 volts, okay, maximum minus minimum. This one in here is also 3 volts. So there is a match between the dynamic range of the ADD and the signal. But what we need to do is we need to shift level this signal in here, pull it so that it's between 1 and 4 volts, okay? And the way to do this, of course, is you come in and you either take the minimum in here to the minimum here, or the center, which is 1.5, to the center of this, which is 2 volts. So, and that's what you need to do. So you need to introduce some kind of common gain if you're using a differential amplifier, or if you're using a single-ended, a DC offset to bring this so that we can see this, okay? So let's take another scenario. So basically your amplifier here, your driver, ADD driver, has to somehow be dealt with like this. So this needs only level shifting. We don't need to amplify, okay? In another case, we might have a sensor between 0 and 2 volts. That's the output of the sensor and the amplifier. And the ADD is between 0 and 4. Now, 0 and 4, the full dynamic range here is 4 volts. And this one in here, the full dynamic range of the signal itself is only 2 volts, which means, unlike this situation, now we have an issue with this signal in here. And it is at the same noise floor of the ADD, so it's correct. But the gain in here is not correct. So this needs amplification. It doesn't need any DC level shifting, but it just needs gain. Okay? And that means these are two scenarios where you can see that one needs level shifting, one needs an amplification. So automatically now you can see that there is a third situation where it involves both. The signal in here that is presented to the ADD from the optical sensor needs level shifting and amplification. And that's this case in here, or one of the cases. There's two cases that this could happen. So what we have is we have a sensor, for instance, from 0 to 2 volts, and the ADD sees from 1 volt to 4 volts. So in this case, we need to shift level this so that this minimum is close to this minimum, and then amplify this so that this here utilizes complete 3 volt range, where this one in here, the span is only 2 volts. This span in here is 3 volts. So this involves both amplification and level shifting as well. So how do we introduce the DC level shifting and the amplification? It's really, when you look at this requirement in here, this could happen where this signal here could be up here, for instance. In that case, you would need to bring it down. And to bring it down, that means to do a negative DC offset. As you can see, all of these involves positive, but it could be above where you need a negative. So how do we do this? If you look at these, that's really what we have. If it involves gain and DC offset, that's the linear, first order linear equation. Basically, it is AX plus B. And that's what we need to do. So our amplifier in here, depending on where the signal range to match the range for the ADD, we really need to pass it through an amplifier, okay, or a differential amplifier, might as well. If you're talking single-ended, it's this. But these here are also can be done in differential, okay? And it's exactly the same idea. And the way to do this is that you've got your output has to follow one of these four patterns. So it's a gain MVN multiplied by the input plus or minus the DC offset, and that basically is what you would need to take the sensor output to make it match the ADD capture range. In first case, let's look at this. This is a positive gain, but a negative DC offset. So the way we do this is we come into the operational amplifier, and since this is positive, okay, so the input, we feed the signal into the non-inverting input. But the DC offset, we put it in the negative, in the inverting port, okay? So basically, in essence, what we have in here, if you look at the transfer function of this, is the V out in here. This Vn, when it goes in here, it sees it's a non-inverting amplifier. So the gain of Vn at the output basically is the ratio R2 to R1 plus 1. And this gets taught in basic electronics. Now, what happened to the reference then? Reference, when it gets to the output, its gain is different than this one, because in that case, it's an inverting amplifier. And the inverting amplifier is just the ratio R2 to R1. And that's basically what it is in here. And of course, it's minus. So this equation in here is a linear equation that has a slope, okay, that it multiplies with Vn, and it has an intercept, a DC offset, that is proportional to this and this two resistors in here. And then likewise, we can come in and say, depending on where the, I think I have a slide. Here it is. Okay. This is a slide where it shows four cases of how this could happen, where you would need, for instance, in this one, you need to add a DC offset, no gain. In this one, you need to add gain. In this one, you need to add both, but this one is the intercepted positive, while the other one, if it's above, you would need. So all of these possible cases, what we want to do, we want to implement them, and here is the implementation for these. So all of this is basically we place the input and the reference, the DC offset in here. And by the way, this reference has to come from the A to D. As you can see in here, in these ones, that reference in here has to be incorporated in here so that we track temperature-wise. Now, let's look at this one in here, okay? So this one here, we need negative slope or negative gain, and then we need a negative DC bias. So, and that basically involves, since they're both negative, then they're both connected to the non-inverting port. And the to the inverting port, sorry. And the non-inverting port is hooked up to ground. And we solve the output. This is just a summing amplifier that has a negative gain. And it's just basically the ratio of this resistor time Vn. That's the MVN. And then the other one is R2 over R3 with the reference voltage, okay? So how do we solve this? Basically, we assume one resistor, and then automatically we can calculate the other one, okay? And that's basically so easy because we know what this one there, we know that if we have a zero input, the V out is only this DC voltage in here. So if we assume R1, then we can figure out what R2 is, okay? And so in that case, actually we verify. If you do that, then this is fixed. It's the other way around, really. What V out you want in here, what is the gain in here? That's you assume 1 plus R2 over R1. You assume R1 and you solve for R2. And once you do that, this is figured automatically, but what happens is that VREF here can be changed to fulfill the requirements of the intercept point. And the way we do that is with a voltage divider. We take the main reference and then we divide that voltage depending on whatever this ratio is. And you can see that they follow these, and four cases is exactly the same. So let's look at this here. This one is both positive. So they're both in the non-inverting port, okay? And of course, you need gain, so we have to have these two resistors on the non-inverting. So how do you solve this? Basically, this is really the summation. The rear reference here is basically going to be, you've got these two resistors, which gives it the gain. So that's here, okay, and it's positive. Plus now the reference voltage in here, basically in here, in this case, it's a little bit different because the DC offset in here is based on its magnitude is based on these two resistors. These two resistors act as a voltage divider. So what we need to do, we need to build a voltage divider, figure out what that voltage is right here from the VREF, and that's basically this magnitude times VREF. And then in addition to that, that's going to be amplified to the output by the ratio of these two resistors, plus one, because it's a non-inverting amplifier. And that's what you see in here, okay? So let's take a first example, okay? So our first example is basically, I grabbed this from the ADI literature and wanted to put it on the simulator, and that's what I have in here. So the first example is very simple. We have an ADD. The reference voltage on the ADD is 5 volts. Okay, and that same 5 volt, we're using it for the amplifier in front. But the requirements on this is that the input range cannot exceed this range in here, which is between above 1.5 volts to 3.5 volts. Okay, that's just the A to D. You can't do anything about this. Okay, the only way to change this is to change the voltage reference in here. But this circuit is operated at 5 volts, and the range is specified to this. And we have a sensor in here that has a plus minus 1 volt. That's the optical sensor, or the overall signal level from the optical circuitry, which might involve transimpedance amplifier. So what we want to do, we want to take this signal out here with this here, and we want to apply one of these cases so that it is exactly matching the dynamic range of the ADD, which means we want this signal in here to be between 1.5 volts to 3.5. And it is a plus minus 1 volt. So empirically, you can see that if the maximum is 3.5 volts and the maximum is 1 volt, that means this signal in here, okay, you have to have 2.5 volt DC so that this signal in here, at the input in here, be in this range. So if you have 1 volt and you have 2.5, that puts you at 3.5. And once it reaches negative 1 volt, from to 1 point, that's 1.5. Now, this voltage usually it's half of the A to D reference. Okay, that's here. So this is really the optimal output what we want. So how do we take plus minus 1 volt AC and give plus minus 1 volt is by having a non-inverting amplifier, which a gain of 1. And the gain of 1, that's what you see these two resistors are the ratio of these two resistors is 1. This is just a terminating 50 ohm in here. And then, of course, now DC-wise, how are we going to go plus 2.5 volts in here? If you do that, that's basically the gain for the input from this port is 1. But from this DC level in here that we want to insert, which is 2.5 volts, the gain in here is 2 because it's this ratio over this resistor over this resistor plus 1, and that's 2. So we want some kind of voltage reference times 2 is equal to 0.5, and that means this has to be half of that, which is 1.25 volts. And that the equations that constrains this is also giving in here. So we have a signal gain in here is basically this, which is minus R2 over R1. And of course, it really doesn't matter it's inverting or non-inverting for the signal because in the DSP, you can always flip that most significant bit and do whatever. Okay, and then the DC gain in here, the common gain, DC wise, it's the ratio plus 1, which is 2. Okay, so let's go and take a look at this circuit. So you can see the circuit in here using the same op amp. We put the DC level in here. And then we put the input signal in here, and we've got these two here, the frequency limiting capacitor in here, and this is the load. Of course, the load in here, this would have to represent the input impedance of this A to D, which is giving. In this case, I just simply said it's 2 kilo ohm. Okay, so let's take a look at this. Okay. Okay, design one. So I close the program. Okay, so that's what we have in here. So basically, I put in 1 kilo ohm in here so that you balance the impedances. That's all I did added. And this is 1.25 volts, okay? And we got this from 5 volts and to the ground in here, okay? So basically, if you look at the, first of all, without signal in here, this output in here has to be exactly 2.5 volts. And you can verify that because it has a gain of 2. You could verify that automatically just saying, and you can see that here it is, okay? So, because this voltage at this point, it's 1.25. So let's look at the AC swing on this circuit. And you can see here that, okay, your input signal is here basically, where it is here, okay, which bounces between plus and minus 1, okay, and the output, of course, it is right here. It's bouncing from 3.5, as you can see, 3.5 in here, down to 1.5 in here, okay? And you can see the DC level is right here, the DC offset, which is 2.5, okay? So that's what we have in here. So let's take another example now. Here's another example, okay? And the other example is basically we've got a signal that is between plus and minus 250 millivolts. Okay, that's from the optical sensor. And we've got an ADD this time that is from zero point 0.5 volts to 2.5 volts. Okay, so the range of this signal in here, as you can see, it's 2 volts, where the range in here is only half volt. So if you look at this here, that means the ADD is wider than this one. So we need to pull the signal, level shift it, so that we can see the range in here. And the way we do this is we really, if it's maximum at 0.25 volts, to get to 2.5, that means we really have to have a DC offset, which is half of this 1.5. And then if it's 1.5, the signal can bounces between plus and minus 1 volt, because when it goes to 1 volt, that's 2.5. And when it goes to negative 1 volt, that's basically 0.5. Okay. So meaning now, when you look at this, and the gain, so what we're going to do is we're going to see what the gain is that will give you plus 1 volt. And that you can see that 0.25 in here, we need 4. So we assume this resistor and that this resistor automatically has to be 4 times that. Okay, and that's this case in here. So this has a gain of 4 right now, according to this equation here. So 0.25 will automatically fall at the desired level that we need. The DC level in here, the gain of the DC level is 1 plus R2 over R1, which is this to this, that's 4. Okay, so it's really 1.5. So which means that the DC voltage has to be at 1/10 of the maximum in here. Okay, and so let's look at put this in the simulator, and this is just numerically showing the you can do a little equation describing this output. So this output is equal to minus Vn with 2000 over 500, which is the gain in here, plus 0.5 in here. Well, this is not the same situation, but we can go ahead. So that's, let's see, is this is for the same thing? Yeah, it's plus 250, plus or minus 250. Okay, so this is a typo here. It's not 0.20. Okay, so 4 times in here plus 2.5, and that means it's going to be between 1.5 to 3.5. That's, I borrowed that equation from the one before. That's this case in here. That's this case. So I apologize. This is not correct in here. Okay, but in any case, so let's go ahead and look at this circuit. All right, so this one is example 2. So let's open that up. Let's close this first. And let's open example 2. Okay, view. Okay, so this is wrong in here. This one, we know that we solved for it, and it has to be 0.3. So this one is 300 millivolts. Okay, so the first thing is let's solve, make sure that okay, so we got 500 ohm and 2K. Let's do the DC analysis first and make sure okay, so we got 1.5 volts. And that's what we said what we need in here. That's the DC offset from this guy. And of course, when we uh, this signal in here bounces is sine wave right now at 100 megahertz with 250 millivolts plus minus 0.25. Okay, so if we run that, uh, okay, uh, okay, so basically the output. Okay.